Let's talk about piecewise functions. Piecewise functions are just functions that are defined by other functions or expressions, but only over specific intervals. Let's look at the notation. It looks complicated, but it's relatively simple. It's denoted by a squiggly bracket, and here we have each expression or formula and their respective interval or condition. Let's take a look at the most common example of a piecewise function, which is the absolute value of x. The absolute value of x will take in any real number and output a positive value. So for example, if we have the absolute value of -5, it's simply just equal to +5. And this goes for any number. If you have a -10, it's equal to +10. But why is the absolute value of x a piecewise function? Let's take a look at the graph. If we look at it, it just looks like two linear lines. When x is less than 0, we can see it just represents the function y equals -x. However, when x is greater than 0, we can see it represents the function y equals x. So if we were to denote this as a piecewise function, it will simply just be f of x is equal to x when x is greater than 0, and -x when x is less than or equal to 0. And we can see this makes sense if we look at the graph. Piecewise functions are multiple functions combined, and they don't necessarily have to connect. So they often deal with a lot of discontinuity. And so it's a good idea to talk about limits. And that's what we're going to do. We're going to look at a couple examples. So for our first example, we're told to graph this piecewise function, which is f of x is equal to x squared when x is less than or equal to 1, and -x plus 5 when x is greater than 1. And we're told to determine the following limits. So let's start by graphing the piecewise function. So we have to graph x squared when x is less than or equal to 1. So here we have 1. At x equals 1, x squared is just equal to 1. And then it will look something like this. And this will go on forever. And now we're told to graph the second part, which is -x plus 5 when x is greater than 1. Not equal to, but greater than. So at 0, it's equal to 5, and then we're going down to the right by 1. And so it's not going to be equal, so it's going to be an open circle, and then it's going to go down by 1 each time. And so it's just going to be a linear line that looks like this, and this goes on and on. So now we're asked to determine the following limits. The first limit is when x approaches -2. It doesn't specify whether it's the left side or the right side, so we're going to have to approach -2 from both sides. So here we have x is equal to -2, and we need to approach it from both sides. So if we approach it from the right side, we can see it's heading towards y equals 4. And if we approach it from the left side, we can also see it's approaching y equals 4. So we can say that the limit as x approaches -2 of our function f of x is equal to 4. Now we're asked to find the limit as x approaches 1 from the left side. So let's take a look. If we approach 1 from the left side, so let's start, it's going to approach y equals 1. So we can say that the limit as x approaches 1 from the left of our function f of x is just equal to 1. But now we're asked to approach 1 from the right side. So let's do that. If we approach 1 from the right side, we can see it approaches 4. And so these two are different. So when we approach 1 from the right, it's equal to 4. Now we're asked to approach 1 from both sides. And so when we approach 1 from the right side, it's equal to 4. And when we approach 1 from the left side, it's equal to 1. And 1 is not equal to 4. So we can say the limit does not exist. So here we have two more examples. So for our first one, we're asked to graph f of x is equal to x when x is not equal to 3, and 2 when x is equal to 3. And we're asked to determine the limit as x approaches 3 of our function. So let's start by graphing it. Here, let's draw our guidelines. And we don't really need to draw any specific points besides x equals 2. And so, or sorry, when x equals 3. And so we're told y equals 2 when x equals 3. And so here we have y equals 2, and we can plot the point. And then we're told y equals x when x is not equal to 3. So x is not going to be equal to 3, and then it's just the straight line y equals x, which just goes up like this. So it's just going to be classic linear line. And we're asked to approach x equals, or we're asked to approach 3 from both sides. So let's do that. So if we approach 3 from the left, remember it's not x equals 3, it's we're approaching 3. We can see that it approaches y equals 3. And if we approach x equals 3 from the left side, we can see that again, it's not approaching 3 itself. It's not equal to 3, but it's approaching it. And we can also see that it's approaching y equals 3. And so we can say that the limit as x approaches 3 of f of x is equal to 3. Now, you may be asking, why is it not equal to 2? Well, if we take a look at our function is equal to 2 when x is equal to 3. And we're asked to take the limit as x approaches 3, not equal. So it will not be equal to 2, rather than 3. Let's take a look at our next example. Our next example is we're asked to graph f of x is equal to x plus 6 when x is less than or equal to negative 2, and x squared when x is greater than negative 2. And we're asked to determine the limit as x approaches negative 2 of our function. So again, let's start by graphing. And so here we have negative 2, and we're asked to graph x plus 6 when x is less than negative 2 or equal to. So here's 1, 2, 3, 4, 5, 6. And it's going to start here and then go down by 1, 2, 3. Okay, so here we have an open, it's equal to, less than or equal to negative 2, so we can have a closed dot here. And then it will just go down from here. And now we need to graph x squared when x is greater than negative 2. And so let's draw y equals x squared. It's just going to be like this. And it's also going to be here. And so it's just going to look like this. And so we're asked to approach negative 2 from both sides. And so if we approach negative 2 from the left side, we can see we approach the y value of 4. And if we approach negative 2 from the right side, we can see we also approach the y value of 4. And so we can just say the limit as x approaches negative 2 of our function f of x is equal to 4. So for our final example, we're given the function y equals f of x, and we're told to evaluate all these limits. So let's start with the first one. We're asked to evaluate the limit as x approaches 2 from the right side of our function f of x. And so here we have x equals 2, and we're going to approach it from the right side. So let's start. If we approach the function from the right side, we can see we approach a y value of 3. And so the limit as x approaches negative or positive 2 from the right side is equal to 3. Now we're asked to approach 2 from the left side. And if we do that, we can see we approach a y value of positive 2. So the limit as x approaches 2 from the left of our function is equal to 2. And now we're asked to approach 2 from both sides of our function. And so as we can see, when we approach 2 from the right side, it's equal to 3. And we approach 2 from the left side, it's equal to 2. 2 is not equal to 3. So we can say the limit does not exist. Let's now do the second question. We're asked to approach 1 from the right side. And so if we approach 1, we can see that we approach a y value of positive 1. Remember, it's not going to be 2 because it's a closed circle, which means at x equals 1, we'll have a y value of 2. And we're not asked to evaluate what our function is at x equals 1. We're asked to approach 1. So it's going to be equal to positive 1. But now we're asked to approach 1 from the left side. So if we do that, we can also see that it's going to approach positive 1. So we can say the limit as x approaches 1 from the left is equal to 1. And now we're asked to approach 1 from both sides. And so when we approach 1 from the right side, it's equal to 1. When we approach 1 from the left side, it's also equal to 1. And these two are the same. So we can say the limit as x approaches 1 of f of x is equal to 1. Now we're asked to evaluate the limit as x approaches 0 from the left side. If we take a look at our function, beyond 0, so when we go less than 0, we don't have anything. Our function isn't defined. And we're asked to approach 0 from the left side, from this side. And our function isn't defined, so this limit also does not exist.